This is John Whitaker for the Mathematical Analysis 1 class, and this is our 34th and last video lecture for this class. And last time we ended with a proof about monotonically increasing functions found on real numbers, or that had real values of their output, and about the left-handed and right-hand limits existing for what they're defined. Today we want to start off with a theorem that is the analogous version of that for monotonically decreasing. And all I'm going to do is state that and give a corollary, then do a little bit more work with monotonic functions, give a few definitions, an example, and one theorem that we'll state without proof, and that will end the class in terms of material. Okay. So here's the analogous theorem to what we had previously. That is, if we let f be a monotonically increasing decreasing. We had about the increasing. Sorry. Decreasing. Let f be, I should say, monotonically decreasing on a to b, this open interval. Then the right-handed limit and the left-handed limit exist at every point x in a to b. More precisely, the infimum over all t values that are sandwiched in between a and x of f of t is equal to the left-hand limit of f at x, which is going to be greater than or equal to f of x, which is greater than or equal to the right-hand limit, which is equal to the sup over all t values in between x and b of f of t. And of course, there was one more statement associated with this. Furthermore, if a is less than x is less than y is less than b, then the left-handed limit at y will be less than or equal to the right-handed limit at x. Okay, so this statement is proven analogously to what we did with the last theorem's proof. As a corollary to these two theorems, it says, let f be defined on a to b, be a real value function not only real value function, but we're going to say monotone. Then, by the previous theorem,
I'm sorry, I'm not paying enough attention. Then, excuse me. Then F has no, that's what I should say, discontinuities of the second kind. And this is a corollary to the previous two theorems. So we'll do a short proof of this corollary. Okay, so here's the proof. Since F is monotone or monotonic, then by the previous two theorems, F of x plus and F of x minus, the right and left hand limits exist for all xn a v. So F has no discontinuities. Of the second kind. Or I guess we had called it second order. Okay, so that is the proof. Next thing we want to do is write up a statement about the discontinuities for a monotone monotone function. It says the following. It says let f be a monotone function on A to B. The set of points So the set of points of A to B at which F is discontinuous is at most countable. So here's the proof. Let F be monotonic on A to B. So here's case one, since it's monotonic. Well, it could be monotonically increasing. So let's suppose that. we let E be the set of points at which F is discontinuous. Note by previous theorem, I guess previous theorems, by previous theorems. No, it's by a previous theorem, because we're assuming it's monotonic, the one we ended with in lecture 33. F of x plus and f of x minus exist for each point any, and not only do they exist, and all we have is f of x minus is going to be less than or equal to f of x plus. Okay. Okay. Now, since really, I said this is for each point in E, but really it's for each point in AB. Okay, that's true. Let's say that. Since E is a subset of A to B, then each point in E is a limit point. Of A to B. Okay. Thus, for each x in E, what we have is f of x minus is going to be less than f of x plus. Now, we had for each guy in our domain that f of x minus was less than or equal to f of x plus. But for the E values, for the values in E, the points in E, it must be just strictly less than, because if they were equal, they'd be continuous. And E's the points in A to B for which f is discontinuous. Okay? So I'll write that down. So if they were equal, then f would be continuous. X. Okay, it's not. So with every point, So with every point x in E, okay, we associate a rational number R of x such that f of x minus is less than R of x, which is less than f of x plus. Okay, look, f of x plus is bigger than f of x minus. And we're thinking of these as real numbers. We're thinking that f grabs a to b and sends it into real numbers, hypothetical numbers. And what we have shown is the set of rational numbers is dense in the real numbers, and so there exists this rational number that's in between these two distinct real numbers. Okay, so we're just picking one rational number in there. Okay, so since x of 1 being less than x of 2 implies that f of x of 1 plus is less than f of x of 2 minus. Okay. We have that r of x of 1 is different than r of x of 2. So what's happening is we have established a one-to-one correspondence between E and a subset of the rational numbers. Okay, since the rational, the set of rational numbers is countable, then any subset of the rational numbers is at most countable. So E is at most countable. Case 2 is that F is monotonically decreasing. This case, I won't do it, works analogously to the previous case. Okay. So we let you fill in those details and have them to prove. like to look at some definitions. So for any real number C, the set of real numbers x such that x is greater than C is called a neighborhood of infinity of positive infinity, and is written, is denoted by C to infinity. So that's what a neighborhood of infinity looks like. Well, analogously, we have a definition for any real number C, the set of real numbers x such that x is less than C is called a neighborhood of minus infinity and is written minus infinity to C. Here's another definition. We let f be a real function. Output values are real values. Defined on E that's a subset of R. We say, so this is about limits, we say f of t goes to A as t goes to x. Okay. Where A and x are elements, they're elements of the reals union plus or minus infinity. If for every neighborhood U of A, there exists a neighborhood V of X such that V intersect E is not empty. It's not empty. And f of t is an element of U, and that is for all t in V intersect T, with t being different than x. So this has to do with infinite limits and limits of infinity, okay? So let me just say that this definition coincides with the definition of a limit of a function given earlier where a and x are considered real numbers. So if you had a and x being considered real number, this would coincide with the definition we gave earlier for limits. Well, I would like to look at one example, then state a theorem without proof, and that is the course. So here's an example. If we let f of t be equal to 1 over t squared, then if you will, f of t goes to infinity. That's a. As t goes to 0. That's our x, 0. And here, e is thought of as the reals minus 0. That's set. So that's where f of t is defined. Okay, so let's prove this. So here we let f of t, we let u be a neighborhood of infinity. What we've got to do is create this v. This neighborhood of 0. Okay. So first of all, what about u? Then u is equal to c to infinity. For some c, it's a real number. So we need a neighborhood of 0, let's say v, such that for every t in v intersect e, which we know to be r minus 0, that's the domain of the function f. F of t needs to be an element of u, so that means it needs to be greater than c. So what we want is that 1 over t squared to be greater than c. So we break this into considerations, cases. And so we have case 1. If c is less than or equal to 0, then we stop and we say, well, note, with t being different from 0, then t squared is greater than 0. So 1 over t squared is going to be greater than 0. So 1 over t squared is going to be greater than c, and that's true for all t different than 0. So our V in this case, the neighborhood about 0, will take it works. Any neighborhood will work. But we'll let V be equal to the neighborhood of radius 1 centered at 0. Okay? And then it gives us what we want. Every T in here, in this neighborhood, intersected with E, which is everything but 0 that's in this neighborhood, then F of that T will be bigger than C in this case. Case 2, if C is greater than 0, we want 1 over T squared to be greater than C. So trying to solve for T here, we want T squared, let's see, 1 over C to be greater than T squared. So we want that the square root of 1 over C to be greater than the square root of T squared. So we want if you will, we want the absolute value of T to be less than the square root of 1 over C. So we want the absolute value of T minus 0 to be less than the square root of 1 over C. If we have this, we get what we need. And so this yields a neighborhood about 0. So we let V be equal to the neighborhood centered at 0 with radius 1, or the square root of 1 over C. And that will work. Now I want to tell you one thing about why we have to split this up into 2 cases. Remember, if C is less than 0, I can't take its square root in terms of a real setting, so I couldn't get a radius here. So that's the reason to break it down into 2 cases. That ends the proof. I didn't go in the backwards direction in terms of satisfying the definition. I'm just telling you these things will work, and our, if you will, our calculations indicate that here. Lastly, we state a theorem. We let F and G be defined on E, which is the subset of R. Suppose that F of T goes to A and G of T goes to B as T goes to X, where A, X, and B are elements of the real numbers, union, plus or minus infinity. Then we have the following. Part A, if F of T goes to A prime then A prime must be equal to A. So even in this setting, the limits are unique. Excuse me just for a second. Thank you for stopping me. That's very nice. 3 more minutes. Sorry. Part B. F plus G acting on T tends to A plus B. F times, this is part C, F times G acting on T goes to A times B. Part D, F over G acting on T goes to A divided by B. And these all were true provided A plus B, A times B, and A divided by B are defined. And I want to say just a little bit more. Note, infinity minus infinity, 0 times infinity, infinity over infinity, and A over 0, if A is different than 0, are not, well, A, no matter what, are not defined. Ladies and gentlemen, we're not going to prove that. Sorry, I didn't turn them. This is the statement. That was C and D up there. I'm sorry I didn't turn it. That's the statement of the theorem. That's the last theorem we're going to present. We're not going to prove it. I thank you very much for your time and patience. That concludes the material for the course.